Yes.
Oh, do you know that university will be started from the 1st of November? Have you heard that?
Yeah, 1st October, 1st November, October. Sir,
Yes, 1st November.
What, sir?
November, November 1st.
November 1st, university will be open.
What time, sir?
1st November.
1st November.
Yes.
November?
November, not October, November. They have given the, after the midterm actually. After the mid, university will open.
All time, how many days go? Only 1 day, 2 day, 3 day?
I do not know about that. But they have said that they will open. They give us a notice.
Sir, I think it's not full open, half full.
What vaccine with the vaccine? How
Sir,
was the vaccine?
Yes.
how about vaccines for you?
Okay, you'll see later what it depends on actually the decision of the government. Okay. What they say, we have to wait for that. Yesterday, okay, let me show you. Okay, that is actually we have started the transmission line from the Simon Ramo. We started, and we have seen the reflection coefficient and the transmission coefficient equations. Today, we'll show you the voltage standing wave ratio. Before going to the standing wave ratio, let's look at another one.
Hello, sir.
Yes, tell me.
So where do we find this lecture slides are videos?
Oh, you need the Google Classroom.
Oh, who else? Right, yes.
Google Classroom.
All right, thank you.
Sir, today we have no Google Classroom.
Yes.
Which time will be upload in the Google Classroom?
Okay, I will upload today. By today, inshallah. After this class.
Okay, sir.
Just knock me. That's how I upload the files. Then I will. If I forget, then just knock me. Okay. Then I will upload inshallah. Okay, let's look at the another topic, which is the ideal line with applied sinusoidal voltage. 1.18. See, 1.18. I'm taking this one from the first chapter of Simon Ramo books. So the title of the topic is ideal line applied sinusoidal voltage. That means whenever you apply the sinusoidal voltage, then what would happen in the transmission line? That will be what I studied today. Okay. So let's look at here. Much of the most practical problems are concerned entirely or at least partially with sinusoidal time variations. If a voltage which is sinusoidal in time is applied at z equal to 0, It may be represented by the exponential. You can represent it by the exponential. This exponential v e j omega t. Okay, but then the corresponding positively traveling wave is written. Then we can write the positive traveling wave like this. And similarly, negative traveling wave like this. So how it would happen? What with the total solution? Total solution would be the summation of the positive and negative traveling wave, which is v is equal to e j omega t plus v plus e minus j omega e z by v omega z by v. This one. Finally, we can write like this. Now, for problems in which we shall be concerned about with sinusoidal quantities, it is not necessary to write the factor e is a omega l. Specifically each time, since it will always be understood that we term are multiplied by this factor. We rewrite 2 and 3. So we can rewrite this j beta z. Rewrite this j beta z. Omega by v is equal to beta. Omega by mu actually. Mu is equal to f frequency. Beta is equal to omega by mu. Omega by v is equal to f lambda. So f will be cancelled. So 2 pi by lambda. Then we can write beta is equal to 2 pi by lambda. After doing some calculation, we can get this one. The rho is equal to v minus by beta. So sigma z divided by 0. Okay. So ultimately, putting this, if we write a factor z is equal to minus l, then you can write like this. Just doing some calculations, we will get one. So these calculations you have to see. Okay, let me discuss it. From here. Ideal line with applied sinusoidal voltages. Okay. Corresponding positively traveling wave is written. See, let me write it here. Say, here the thing, b plus e to the power j omega t minus z by v, that is positively traveling wave. And what will be the negatively traveling wave? E j omega okay. So what then? What is the summation? E plus j omega e minus z by v plus v minus j omega e plus Now, if we take the j omega common, if we take the e j omega t common, then we can have like this. Plus z into omega z. So here you have to if I want to keep the omega, okay, z and like this. Okay, then after that for the current, we take it. And we write this one. E equal to b plus e j is equal to z plus b minus e j. Okay. It is not necessary to write this one every time, each and every time. So instead of this, we can write only these equations. Then we take omega by b, omega equal to 2 pi f divided by b. Is equal to f lambda would be f would be answer 2 pi by lambda would be there. The quantity beta is called the phase constant. Here beta is known as the phase constant of the light, since beta z measures this instantaneous phase at a point z with respect to z equal to 0. So beta z means beta z measures the instantaneous phase at a point z with respect to z. So you have to calculate this one. Here, look at here. Moreover, if voltage and current are observed at any point z, they will be found exactly the same at point such that because it differs from that of the first point by multiples of 2 pi. The distance between points of like current and voltage is called a wavelength lambda by the foregoing reason. So as you know, we have found this equation. Beta is equal to 2 pi by lambda, which is known as the phase constant. Here the beta is known as the phase constant, and the equation of the beta is 2 pi by lambda. Okay, so lambda is the wavelength here. So do you remember what is the wavelength? If you don't, let me show you that what is the wavelength. Look at this sinusoidal wave. From this point to this point, that is wavelength. That is lambda. Moreover, from this point to this point, that is another lambda. So these are the wavelengths. Okay, so these are the wavelengths. Okay. Now finally we can write the rho is equal to v minus by v plus. Rho is what? Rho is actually the reflection coefficient, which can be referred as the ratio of the reflected wave to the incident wave is known as the reflection coefficient. Reflection coefficient. which denotes by the symbol rho, small rho. So the equation would be look like this: ZL minus ZL divided by ZL plus ZL. ZL plus ZL minus Z0 divided by ZL plus ZL. Okay, so that is the equation of the rho. ZL minus ZL divided by ZL. Okay, now here look at the equation. Input impedance. Input impedance is actually the what? Look at here. Dividing 4 by 5. So here is the equation impedance. 4 and 5. This equation, if you divide this one, then you get the input impedance. Look at here, one thing. So if we consider ZL, here it is, that not. So here, in this portion, there is an impedance which is ZI. That is the input impedance. That is the input impedance. This one, input impedance. Input impedance. Input impedance. That is the load impedance. Load impedance. The load impedance, that is the characteristics impedance. Characteristics impedance. The three kind of impedances are there. So here we are talking about the input impedance, which is the ZI, which denotes as ZI, and ZI is equal to V by I. Here is a V and here is the I. So if you divide this one by this, then we can get this one, get this equation. Okay, then you will get this one. Zi is equal to Z0, J beta plus rho E minus J beta. This one. Now, what will happen? You have to elaborate this equation. These two equations are known as the Euler theorem. Let me show you what is the Euler theorem. Do you remember this one? I don't know. Function J theta is equal to cos theta plus J sin theta. And e to the power minus J theta. What? Cos theta plus J sin theta. Cos theta minus J sin theta. These are known as the Euler theorem. Okay, so if we look at here, that instead of theta there is beta. Instead of theta we have the beta. So they have used the beta. So then here instead of rho, we can write beta minus z naught divided by beta plus z naught. Okay, beta plus z naught. Then they have calculated this one. Finally, they got this. Here, that is the equation. It is the input impedance equation. Similarly, instead of Zi, if we write the admittance, then we will get this one. For the admittance, we will get the same equation. So that is the input impedance equation. That is the input admittance equation. Okay. Now look at some problems. Let us look at some problems regarding this. Find the special cases of 10. This one for a shorted line, an open line, a half wave line with impedance ZL. Quarter wave line with impedance ZL. You see. So do you guys have any idea about this problem? For a shorted line, if the line is short, then what would happen? ZL would be 0. If the line is short, then ZL will be 0. So if the ZL is 0, this term will be 0 and this term will be 0. So only this one and this term will be there. So when first condition here, when ZL is equal to 0, that is the shorted line. In that case, Zi will be like this. Z naught. This one 0. This one 0. Z0 will cancel out. Sin beta. They would be there. They would be there. Sin beta. And cos beta. So equation will be Z naught 10 beta. Z naught 10 beta. Okay. So for the shorted line, open line. Open line means infinity. Z will be infinity. Okay, so Z will be infinity. In that case, cos would be there. Cos by sin would be there. And this one will be unnecessary. So it will be cot. Okay, and then half wave line means for the half wave is lambda by 2. What is lambda by 2? L is equal to lambda by 2. For the half wave, L is equal to lambda by 2. Again, beta is equal to 2 pi by lambda. Beta is equal to 2 pi by lambda. L is equal to lambda by 2, half wave. So lambda would be cancelled out, 2 would be cancelled out. Pi would be there. So cos pi sin pi. Open line, cos pi sin pi. For a half wave line, impedance ZL. Quarter wave line means impedance would be lambda by 4. lambda by 4. Impedance would be lambda by 4. In that case, lambda by 4 into 2 pi by lambda. Lambda will be cancelled out. So that would be pi by 2. So cos pi by 2, sin pi by 2, this calculation will be required. That's how we can calculate this one. I think you can solve this one. And this one also important. Point to transmission lines have to be connected in cascade. A reflection of the wave is transmitted from one to the other will occur if they do not have the same impedance. Show that a quarter wavelength started between the cascaded lines because the first line to see is zero as transmission. Thus, remain reflection in cos square. If beta into pi by 2 z naught 2 where z naught is at the impedance of the quarter section at the final line. And another one, a receiving line of negligible loss is 1/3 of the wavelength long and has a capacity impedance of 100 ohms. The attitude receiver acts as the load. Like find the input impedance, sketch phasor diagram showing the values of V minus, I plus, I minus. Both input, check the calculated results for impedance from this diagram. Okay, you have to check these problems. Okay, now let's move on to another one. A standing wave ratio. Okay, so what is the standing wave ratio? We have discussed this I think. Standing wave ratio. Let me show you again. Say if we consider a pitch of transmission line, if let us consider a pitch of transmission line here. This is the incident wave. That is incident wave. That means the B plus. That is reflected wave. That means the B minus. Okay. So two kind of waves are there. So as a whole, you can see this. As a whole, we can see the standing wave. These two waves creates another thing, that is the standing wave. So this is the standing wave. In this standing wave, this is the V mean, that is a V max. That is V max. V mean. So what is the result? Result is AC is equal to V max by V mean. V max by V mean. Okay. That's the V max by V. S is equal to V max by V. This S is known as the voltage standing wave ratio. See, the first becomes increasingly negative in phase as that increases. The second is increasingly positive. There must consequently be some value of Z for which the two terms are of the same phase. Their amplitudes then add directly. So amplitude at directly at this point there is maximum. So that is the maximum point where the amplitude of the 2F at directly. The quarter wavelength from the position just discussed say the first term will have decreased phase by pi by 2 and the second will have the increase by pi by 2. So that the two are done by apart in phase, they subtract and given minimum amplitude of the mode. So minimum amplitude will be there, V plus minus V minus. The standing wave ratio is then defined as the ratio of the maximum voltage amplitude to the minimum voltage amplitude. So a standing wave ratio is then defined as the ratio of the maximum voltage amplitude to the minimum voltage amplitude. So S into V minus V. So we can write like this: S equal to V plus V minus by V plus minus V minus. So if you divide it by V plus, then you will get this. Or rho is equal to S minus 1 divided by S plus 1. Okay. So I meaning is equal to V plus minus V minus by Z naught. So Z max. So another term will come here. So what is the I mean? Minimum current. Because of the negative sign appearing in the current position, it is evident that at the position where the two traveling wave turns and in the voltage relation, they subtract in the current relation. So, and vice versa. The maximum voltage position is then the minimum current position. So maximum voltage position will be the minimum current position. So V plus minus V minus divided by Z naught. So we can show this Z max, Z is equal to Z naught divided by this. So Z naught S. If it is purely resistive and has the maximum value it will have at any point along the line. And what would be the VMI max? The position of the voltage minimum, current is maximum. The position of the voltage minimum, current is maximum, and the impedance is minimum here. So I max is equal to V plus by V minus Z naught. So Z min is equal to this. Z naught by S. Now here some problems are there. And the impedance of 100 plus 300 ohms is placed is the low transmission line in 50 ohms. Find the reflection coefficient, impedance, magnitude, and phase and standing wave ratio of the line. So whenever we check out the problems, then we will find out this. Okay, so these are the values. Here you trigger this one. Z max, Z mean. Z mean is equal to Z naught by S. Z max is equal to Z naught into S. And what is the S? S is equal to 1 plus rho divided by 1 minus rho. And what is the value of rho? Rho is equal to S minus 1, S minus 1 divided by S plus 1. Okay. That's how you can find out the value of rho here. S and rho. Here. S is equal to 1 plus rho conjugate not the magnitude, magnitude of the rho, 1 minus magnitude of the rho. And rho value is s minus 1 divided by s plus 1. This is actually magnitude. Rho can be written as like this. Rho can be written as r angle of theta. That means there will be an angle, or it is a complex number. Rho is actually a complex number. So this thing is the magnitude of the rho. That is the magnitude of the rho. That is the angle of the rho. Okay, like this. So whole thing. That is the whole thing. Okay, so I think you have understood that how to calculate the rho the diffusion coefficient, and how to calculate the standing wave ratio from the rho. So let's look at the problem here. Some problems are there. An impedance of space as a load and transmission line and impedance as a see here in this problem what they given ZL we have 100 plus J of 100 J of 100 Z not 50 ohm, Z not 50 ohm. Find the reflection coefficient. Coefficient, magnitude, phase and standing coefficient. Okay, so reflection coefficient. What is the reflection coefficient? So if we want to calculate the reflection coefficient, so let me do it. ZL minus Z naught divided by ZL plus Z naught. So you put the value. ZL is what? 100 plus J100 minus 50. 100 plus J100 plus 50. So ultimately, if we do the calculation, then we will get what? Let me find it for you guys. I am using the calculator now to find it out. The value is 50 plus J100. 50 plus 100. Divided by 150 plus. What we have got? 0.54 plus 0.31. 0.31 J. So we have got this, but we have to convert it to the polar form. So you have to go to the polar form. 0.54, 0.31. So what is the equation of finding out the polar form? So do you remember the equation? Complex to polar. There is a formula. So we have to find out the R. We have to put the square root of 0.54 square whole square plus 0.31 square. That's how we can calculate. And to find out the angle, theta, that is the formula, tan inverse d by a. Tan inverse d by a. So here is the formula. We do it. 0.5 square plus 0.62, 0.62, and the angle will be tan inverse d by a, that means 0.31 divided by 1.4. 29.86. 29.86. So that is the value of. Okay, you got it. Because so finally you can write 0.62 if we want to convert it to the polar form, then 29.86. That is the polar form. And here the magnitude, that is the magnitude. That is the phase. Okay. And standing wave ratio, how to do it? X is equal to 1 plus rho divided by 1 minus. So just put it here, 1 plus 0.62, 1 minus 0.62. You do not need to calculate the angle here. So 1.62 divided by 1 minus 0.62, then it would be 4.26. So that is 4.26. That is the answer of this one, this problem. Okay. So we have seen so far these two things. These two are really important things. So we have to calculate this one. Okay. So in the next class, we check out the Smith chart.
Okay, sir. Inshallah.
Check out the Smith chart. Next class, we'll finish it, inshallah.
Okay, sir. Send PDF, inshallah.
Inshallah. So let me take your attendance here.
Okay, sir.
Have you got your result?
No, sir.
No, sir.
Okay.
Sir, and sir, our coordinator said I'm a little bit sick, so I didn't finalize your result. He said that. So we're waiting.
Okay, roll number 2, 14, 9, 1, 18, 10, 12, 17.
14, sir. 14.
Yes, 14. 2,
Also two
Two.
present, yes, sir.
2, 14, roll 9, 1, 18, 10, 12, 17.
Also one, Diva present.
Yes.
Okay, sir. Okay.
Okay, anyone left?
No.
Person.
Present.
1, 2,
Diva present.
3, 4, 5.
Control system ke kan semua gitu.
Yeah, 8 person are there.